Chapter 5, Lesson 2 of Advanced Algebra. We're working with quadratics, and I want to do a few word problem examples where we apply quadratics to determine the max or the min. And these problems may be involved in finding the maximum of two numbers multiplied together or the minimum of two numbers multiplied together. A lot of the problems are talking about the maximum perimeter that you can enclose given a certain length of fencing. What happens if you throw a ball, just over a fence, and where is it going to land, and what's the equation for that? These are all very common types of quadratic problems. So I want to cover a number of these in this video, and you can hopefully this will be helpful to you as we move forward. Again, the quadratic equation that we're looking for is ax squared plus bx plus c, and this is the standard form, but in this lesson we talked about this form y equals ax squared plus c, where there is no linear term, and most of these questions that I'm going to deal with in this lesson are going to end up being in this form right here. We'll deal a lot more with this other form in later lessons. So the equation, remember, as I just said, is y equals ax squared plus c, and this is a quadratic where we have an x squared term. So the goal in all of these word problems is to create an expression that has an x squared term in it. And again, remember we've talked about in the last video where we just need to determine what a and c are, and we can do that by, if we have 2 points that we know that we can substitute in. So as we're writing these equations or looking at these word problems, those are the types of things we want to do. Now, the toughest thing about word problems is getting the expressions together and what we need to do so that we create these quadratics. And we're going to be using substitution quite a bit because most word problems are given in the form of formulas that you need to know. And in this formula, or in this lesson, we're dealing a lot with squares and rectangles, and we're talking about perimeter. So we need to remember that the perimeter is equal to 2 widths plus 2 lengths, whatever those are. Another type of problem that we're going to deal with is area, again, of rectangles, which is lengths times width, or base times height. And these are formulas that you need to remember. And we're going to use these formulas, substitute in values that we know, or at least that we are given in the problem, and then we're going to have to manipulate these algebraically in order to do these. So I know there's kind of a lot of intro, and I think the best way to do this is probably just to do some problems for you, and we'll go from there. So the first type of problem I want to do is where we're given a description of two numbers. So if you're looking in your book, or like page 248, number 35, where we're given a pair of numbers whose sum is 26. So we want two numbers whose sum is 26. Okay, so that's the first thing, and again, that's the English representation. What's the math representation? So, well, two numbers that we don't know what they are, so we'll call them x and y, is equal to 26. So we know that from the expression. Now, as always, when we're given this, it's really not helpful to us to have both variables on one side. So solving this algebraically for either x or y is going to be what we want to do. So, and we're going to want to do that whether we're dealing with perimeter area. Always solving it for one variable is a tool that we want to use, because then we can substitute it in when we know another equation that has the same value. So if we were to solve this for y would be equal to 26 minus x. And again, I now have an expression for y, so if I have a second equation that has a y in it, I can substitute this in instead. The second part of the problem says that the product of these same two numbers creates a maximum. So if I took these same two numbers, and then that creates a maximum value. Now what is that maximum value? We don't know. Now again, here's a second equation, x times y equals some maximum, but now I know what y is. It's 26 minus x. So if I substitute this in, x, and then instead of y I put 26 minus x, and that's going to equal some maximum value. Well, now you'll notice if I distribute this out, 26x minus x squared, what do I have right here? I have a quadratic equals some maximum number. I have the quadratic expression, which is going to create a max or a min. So now I simply compute the max or the min either algebraically. Remember the opposite of b over 2a giving us the x value, then substituting that into this expression giving me the y value. Or I can put this in my calculator, 26x minus x squared, and calculate the max that way. So the idea here is to take these English expressions and turn them into mathematical expressions. And again, I create two equations, which then I can use substitution to create my quadratic, which is what I need. So that's one type of problem that you'll have to do. And again, remember, the whole key to this is just creating these equations, translating the English into math, and then using some algebraic manipulation to create other things that we need. A second type of problem is very common, is to create or to give the maximum volume or maximum perimeter or maximum length and width of a square or rectangle given a certain amount of material that produces the largest or maximum volume or perimeter. So for example, if we're looking at number 41 in our book, page 249, it says that suppose you want to create a frame for a collage of pictures and you have 9 feet of wood. So we have 9 feet of wood that we're going to create this frame. What's the dimension of the frame that would give me the maximum area? Okay, so I'm going to create this frame that's going to give me a maximum area. Okay, well, area I know is the length times the width. Okay, again, well, this is two variables that I don't really know much about. So all I have is L and W, but again, I can create an equation given the fact that I know what area is, length times width. Now, this really doesn't help me because, again, I need to create this quadratic where I multiply length times width, but the L has to have a W in it, or the W has to have an L in it so that it creates that quadratic. Now, whenever you're given this, let's write an equation of something I know. Well, 9 linear feet of wood is going to enclose this frame, so that's going to be the perimeter. So I know when I add 2 W's, okay, and 2 L's together, and I know this isn't a scale, I know that the perimeter is going to be equal to 9 because that's how much feet I have. That's how much feet I have. That's how many feet of wood I have. So the perimeter is going to be 9 when I add 2 widths and 2 lengths together. Now again, this is an equation that I can solve for W or for L, and again, which would then create something that I could substitute into this expression, giving me a length times a width, which is going to create the quadratic. So let's just solve this for W. So 9 minus 2L then is going to equal 2W, and then dividing both by 2, so 9 halves minus L is going to be equal to W. And again, now that I know what W is, I can substitute it into my expression. So the area, the maximum area, which is what I'm looking for, is going to be the length, which I have, times W, which I now know is 9 halves minus L. And again, if we distribute this out, you'll notice that we have a quadratic right here. And now all I need to do is find the max or the min. And again, I can calculate this algebraically or put it in a calculator and find the maximum value. That's going to give me the maximum area as well as the x value or the L value that would need. So whenever you're given a length of wood, you want to use the perimeter equation to then simplify that you can then substitute into the area equation that allows you to determine what you need to do. Again, a very common problem, something that you'll need to repeat over and over. So let me do one other type of problem, or explain one other type of problem that you'll have, and that is when you describe someone throwing a ball or something like that. And if you think about throwing a ball, the ball has a very nice parabolic trajectory. When you throw a ball, it reaches a height and comes down. So if you have a person standing here and they throw a ball, you know it usually goes up and it comes down and it lands. Well, that's a very nice upside down parabola. And one of the things that we want to do in common is to put this parabola in a coordinate plane. In other words, if I put and draw this parabola right here, if I put the vertex right here at the maximum height of the ball when someone's throwing it, well, I know the coordinate of this right here is going to be 0, because on the y-intercept the x value is always 0, and then if I know the height, I can just put the height right here. And I'm usually given then also a place where it lands, so I'm going to know this distance is going to be the x value, and then the y value is going to be 0. So I create those 2 points that we just talked about earlier, where we substitute them into the equation, and then we can use substitution or elimination to determine the value of the equation. So whenever you're given a problem like that, it's simply taking the parabolic trajectory, or even if you're talking about the shape of a satellite dish, locating it in the coordinate grid where the maximum value is on the y-intercept, and you know the length and the diameter of that, that allows you to use this quadratic equation then to write a formula for that particular situation. So for example, in number 42, on page 249, it says, suppose you throw a ball over a 10-foot fence and it barely clears the fence and it reaches its highest point directly above the fence. So again, you're standing here and you're throwing this ball and it just clears a 10-foot fence. All right, well, if I make that my y-axis, okay, then I know the coordinate of this point right here is 0, 10. Whoops, not 0, 0. 0, 10, I know one point of my equation, and I also know it's the y-intercept, so I know that the c value is going to be 10. Further, it says that the ball lands 10 feet from the fence, so as it goes out here and the ball lands, it lands 10 feet from the fence. So I know this distance is 10 and 0. Well, now I have my second point, which I simply substitute into my expression and create the equation. So again, it goes back to what we did in the last video, but we're just now applying this to word problems. And that really is the key to word problems, is simply doing what we've done in those other problems, just extracting these points from the word problems as we apply it to real life situations. Okay, so I hope those were helpful for you and can help you tackle some of those problems, and we'll look forward to seeing you in class.